We are on a quest to understand carbon a whole lot better. To do this, we have to mention the different forms of carbon, and to understand the different forms of carbon, we must learn of the phenomenon called allotropy. The idea of allotropy was first introduced by Swedish scientist Jacob Berzelius in 1841. He got the name allotropy from the Greek word allotropia, meaning variability or changeableness. You see, in simple terms, allotropy is a phenomenon whereby an element can exist in different forms but all in the same physical state. What we mean is that sometimes an element can exist in several forms. Think about it this way. Water may be ice or steam, but it does not change the fact that it is still water. This does not mean that water exhibits allotropy, because first of all, water is not even an element, and its different forms do not exist in the same physical state. I just want you to understand that one substance may exist in different forms. Now that this is clear, we say that an element exhibits allotropy if it can exist in different forms, but with all the forms in the same physical state. The different forms of elements that exhibit allotropy are called allotropes. Allotropes of an element usually have different physical properties. Most times they differ in color, shape of their molecules, and even electrical conductivity. Their chemical properties may be similar to an extent, but also different. Several elements in the periodic table exhibit allotropy. Carbon, phosphorus, sulfur, and oxygen are common examples that come to mind when we talk about elements that exhibit allotropy. Since we are looking at carbon particularly on this quest, we will be looking at the allotropes of carbon, their properties, and their uses. But before we go there, it is important to understand that because of the many allotropes of carbon, we've decided to group them in two. They are the crystalline allotropes and the amorphous allotropes. In our lesson on solids, we saw that solids may be crystalline or amorphous. We explained that crystalline substances are substances with a very strong intermolecular force holding its particles together. These strong intermolecular forces keep the particles very well arranged in a well-defined geometric structure. Carbon has two crystalline allotropes. They are diamond and graphite. Yes, diamond is a form of carbon. We'll look at it in depth later. Let's continue. Carbon also has amorphous allotropes. Of course, amorphous substances are very different from crystalline substances. Their forces holding their atoms together are much weaker than those in crystalline substances. Amorphous solids are rigid structures, but they lack a well-defined structure. They usually have spaces in their structure and do not have a particular geometric shape. There are several amorphous allotropes of carbon. They include coal, carbon black, charcoal, and coke. Do not worry, in subsequent lessons we will discuss these allotropes in depth. For now, ensure that you remember what we've said about allotropes and the classification of allotropes. In case you've forgotten, we said that allotropy is a phenomenon whereby an element can exist in different forms but all in the same physical state. We also classified allotropes of carbon into crystalline and amorphous allotropes. We said that the crystalline allotropes consist of diamond and graphite, while the amorphous allotropes consist of coal, carbon black, charcoal, and coke. See you in the next lesson.